Consider the simplified block diagram of an optical communication system as shown. We transmit binary data by pulsing a laser or a light-emitting diode, LED, in free space or coupled with an optical fiber. If we want to transmit a binary 1, we switch on the light source for t seconds. For a binary 0, the light source is turned off for the same time period. In optical communications, this is known as on-off keying encoding, or for short, OOK. Clearly, the rate at which we can transmit data in this manner is limited by the rate at which the light source can be switched on and off. Since most lasers and LEDs can be switched at speeds of hundreds of megahertz, a simple procedure like OOK can yield data rates of up to gigabits per second. This is the reason technologies like free space optics are important for 6G and beyond. Let us return to our current system. At the destination, the receiver converts this optical signal back into the original string of binary numbers using what is known as a photodetector. The received light signal hits a photoemissive surface, which then emits electrons randomly. This follows from Albert Einstein's well-known photoelectric effect. The number of electrons emitted during a t-second interval is random and needs to be described by a random variable. Therefore, let us define a random variable x as the number of electrons counted during the t-second interval. X is described in terms of two conditional probability mass functions, PMFs, which we write as follows. We know from probability theory that if a random variable represents the number of independent events occurring in a fixed time interval with a known constant mean rate, then x must follow the Poisson distribution. We can actually show through a quantum mechanical argument that these two PMFs should be those of Poisson random variables. Note that when a binary 0 is sent, a relatively low number of electrons is typically observed, whereas, when a 1 is sent, a higher number of electrons is typically counted. In particular, suppose the two probability mass functions can be written as shown. In these two PMFs, the parameters beta0 and beta1 are interpreted as the average number of electrons observed when a 0 is sent and when a 1 is sent, respectively. We assume that beta0 is less than beta1 because when a 0 is sent we tend to observe fewer electrons than when a 1 is sent. At the receiver, we count the number of electrons emitted during each t-second interval and then must decide whether a 0 or 1 was sent during each interval. Suppose that during a certain bit interval, it is observed that k electrons are emitted. A logical decision direction would be to calculate the following probabilities and choose according to whichever is larger. In other words, we calculate the a posteriori probabilities of each bit being sent given the observation of the number of electrons emitted. We then choose the data bit that maximizes the a posteriori probability. This is known as a maximum a posteriori, MAP, decision rule, and in this case we decide that a binary 1 was sent. As we can see, these desired a posteriori probabilities are backwards compared to how the photodetector was statistically described. What I mean is, we know the probability of x being k given that a binary 1 was sent, but we want to know the probability that a binary 1 was sent given that x is equal to k. We will now use Bayes' theorem to help us convert what we know into a result we desire. Using the law of total probability, we obtain the following result. Therefore, applying Bayes' theorem, we obtain the following probabilities. Since the denominators of both a posteriori probabilities are the same, we decide that a 1 was sent if k exceeds the expression given, otherwise we decide in favor of the binary 0. Therefore, our optical communication system counts the number of electrons emitted and compares that number with a threshold. If the number of electrons emitted is above the threshold, we decide that a 1 was sent, otherwise, we decide a 0 was sent. Incidentally, we are also be interested in evaluating how often our receiver makes a wrong decision. Ideally, the answer is that errors are as little as possible, but still we would like to quantify this. In the next video, we will take an in-depth look at how to derive the probability of error, a crucial performance metric for communication systems. Thank you for watching our video. Please don't forget to subscribe. See you next time.